Hello, we're Group 6, and our project is using MPC for minimizing HVAC system energy consumption and peak power load. Contemporary HVAC systems tend to use on-off control, and while this is easy to implement, it's not very useful with regards to thermal comfort or peak energy consumption. As such, we designed an MPC controller, which can be split into three parts: system model identification, cost function design, and our results versus a PID controller.
First of all, we need to figure out what is the system model for the MPC. We use RC circuit analogy to represent the heat transfer equation of a building. Then we discretize this equation and transform it to a simpler expression using A and B. Secondly, we constructed a building thermal model in MATLAB for simulation as well as the A and B parameter estimation. The original MATLAB model doesn't include building thermal mass, so we added an equivalent air thermal mass into the model. This is the simulation result of the MATLAB model. The default control logic causes frequent on and off cycles, and the thermal mass affect the response frequency of the indoor air temperature to the HVAC systems and the outdoor air temperature. Thirdly, we use the least square regression approach to estimate the A and B parameters in our system model. We populated this estimation error using the simulation data from MATLAB. As you can see in the graph, the estimated data perfectly matches the simulation data. Therefore, we assume the model we used in the MPC is same as the model we use for simulation.
So this is how we set up our MPC cost function. We want to minimize the summation of energy inputs and temperature violations, and it's weighted by K and rho. The cost function is subject to the following equality and inequality constraints. The equality constraints is obtained from our discretization. We use several different disturbance decay in our simulation, and decay is based on the different people loads. T underline and T over bar represent the lower and upper bound of zone temperature, which we set to 20 and 22 degrees centigrade. Any T outside this bound will cause higher costs. Epsilon underline and epsilon over bar represent the lower and upper bounds on temperature violations, which are the sub-constraints in this model. They can be changed to a single set point by using T lower equal to T higher.
We ran several simulations using our MPC controller with different disturbance profiles. We set the comfort range to 20 to 22 degrees Celsius. In this first simulation, we introduced a small 20 kilowatt load with a constant outdoor temperature and an initial zone temperature of 22 degrees Celsius. The MPC controller predicted the upcoming disturbance and pre-cools the zone to under 21.5 degrees Celsius before the 20 kilowatt load takes effect. This results in the zone temperature staying within the comfort range for the entire simulation. With a larger 100 kilowatt load, the MPC controller implements a simpler pre-cooling strategy, but the input constraints prevent the zone temperature from staying entirely within the comfort range. The MPC controller actually pre-cools below the 20 degrees Celsius bound due to the upcoming large disturbance. When we remove the input constraints, the MPC controller is much better able to keep the zone temperature within the comfort zone. Because of its ability to input more power, the pre-cooling begins at a later point than in the previous constrained simulation.
Here we compare our MPC controller with a conventional PID controller. Since the PID controller has no predictive elements, we can see that the sudden load increases the temperature much more than in the MPC case. Finally, there are some improvements we can make to our MPC controller to ensure its robustness. First, we could implement and tune an integral control to help deal with constant disturbances not within our model. Secondly, we could analyze our A and B values utility when derived from a much more complex system than a simple thermal circuit. If there's significant model mismatch, then we'd have to improve our controller to account for it. And finally, we have to test more realistic disturbances, such as people entering a room at a certain rate rather than all at once.